So again, I want to just say good evening to everybody. I'm Joe Deli Carpini, the Science and Operations Officer. So I will be presenting solo tonight, a little bit different from the past. Rodney Chai helped me put this presentation together, and he ended up working a couple of late nights. So we gave him the evening off and let him take it easy. So I figured I could handle this pretty much myself. So as always, if you have questions, go ahead and use the chat box, which is in your control panel on the right of your screen. I will answer as many of those as I can at the end, and we'll also have a weather briefing as we normally do, so you'll want to stay tuned for that. So to start off, a little bit of history on the Jetstream. We did a little research on this, and in fact, it goes back to 1883, the eruption of Krakatoa way out in the Pacific. There's some records that weather watchers tracked and mapped the effects on the sky over several years. And they labeled the phenomenon equatorial smoke stream. So those were kind of the first indications that there were some sort of strong winds aloft. And then in the 1920s, there was actually a Japanese meteorologist, Wasaburo Oishi, and he detected the jet stream from a site near Mount Fuji using pilot balloons. So think kind of like our upper air balloons that we use today. As they rose into the atmosphere. But his work, as it says here, largely went unnoticed outside of Japan because it was published in Esperanto, which is a language that was not very well known at the time. So even here in the United States, his work was largely ignored. In 1933, an American pilot, Wiley Post, made several attempts at a high-altitude transcontinental flight. And he noticed that at times his ground speed greatly exceeded his airspeed. So he was like, well, something's up with that. So he kind of made some observations. And then in 1939, there's a German meteorologist, and I'm going to try and pronounce this, Heinrich Seilkopf. He's credited with coining the special term in German, which means jet current, for the phenomenon. So this really dates back, starting the late 1800s, but really the first part of the 20th century was when we really started to get a better understanding. And then moving forward for the United States, it was really during World War II. That the jet stream came into play. The B-29 pilots flying toward their targets in Japan discovered their cruising altitude winds were as high as 230 miles per hour, and the wind caused their bombs to miss targets, and really the headwinds ended up requiring the bombers to use more fuel than expected. So in some cases, so much more that they ran out of fuel on the return trip. So obviously that's very dangerous. So it was really World War II here in the United States where we really started to study the jet stream and kind of understand, kind of how it worked. So what is a jet stream? So definition, it's strong winds concentrated in a narrow stream in the atmosphere. Normally, it refers to high-altitude winds, and that's really what the talk tonight is going to focus on. But I'll talk a little bit about low-level jets, too, and that's a jet stream known at lower levels of the atmosphere. So upper-altitude winds, we're talking 25, 35, 40,000 feet, and then the lower-level jet is somewhere between maybe 2,000 and 5,000 feet. So we'll talk a little bit about both, but mostly focus on the high-altitude jet. So the position and orientation of these jet streams vary from day to day, and by looking at their pattern, we can understand general weather patterns, hot and cold, wet or dry, which are closely related to these positions. And we really have two jet streams that we talk about. One is the polar jet stream here on the north, and then the subtropical jet stream here in the south. And both hemispheres have these features, polar and subtropical. So obviously during the winter, this polar jet comes more into play. It dips a little bit further south. In the summer, our subtropical jet stream comes more into play. The polar jet retreats more to the north. So what is it and where is it located? It's located at jet level, as the name kind of implies. So it's typically near the upper end of the troposphere. And if you remember, if you've been to some of our talks before, the troposphere is the layer in the atmosphere where weather happens. So once you get above the troposphere, you get to the stratosphere. The air is a lot more what's called stable. Occasionally, you can have some thunderstorms punch into the stratosphere, or you can have in winter storms that are very strong, say like our blizzard of 2018, stratospheric air can actually get into the troposphere and really help energize a weather system. But for the most part, the jet stream does remain in the upper part of the troposphere, and this is the altitude where most of our commercial aircraft fly. It saves money in a way. If you can take the jet stream from here to Europe with a tailwind, you're going to save on fuel costs. So it kind of makes sense to fly at that altitude. So a little bit of a cross-section is actually circulations associated with the jet stream. They're not just rivers of air that go west to east, they actually kind of work in the vertical too, and we'll talk a little bit more about that when I talk of low-level jets, but they actually induce rising and sinking motion. So we're looking at a kind of a shot of the globe here. You can see the polar jet stream to the north, located kind of at our latitude, and then the subtropical jet stream located to the south. But you can see these circulations that work around it. So you have polar air coming down, obviously from the poles, and this actually forms an area of low pressure on the polar jet. So the air is rising, and eventually it expands outward. So think of this as kind of almost like a large-scale sea breeze circulation, where you've got this kind of circulation of air, and it works the opposite way off of the subtropical jet stream, where you have high pressure. So it's bringing warmer air up, that air rises, cools, and then heads back. So you've got these two circulations that go on. You've got a transport sometimes of colder air coming in and a transport of warm, moist air coming in. And those are the ingredients that we see a lot of times for our winter storms. I should mention, this time of year, the summertime, the atmosphere is known what's kind of in thermal mode. So the jet streams do have some influence, but we don't have big temperature differences in the summer like we do in the winter. So in the wintertime, these jet streams have much more of an influence on our day-to-day weather than they do in the summertime. Summertime is more local effects. Think of thunderstorms and things like that. So in a cross section, this is kind of what the jet stream looks like. This is an example looking from Bismarck, North Dakota on the left, across Denver, the Rocky Mountains, and down over to Yuma, Arizona. So winds, as you can see, increase toward the core of the jet stream. And the height of this core will vary, but look how broad it extends, both in height, going up in the atmosphere. Again, it's roughly 30,000 feet to 50,000 feet, somewhere in there. It varies, but also in length, going from North Dakota all the way down across the country. So jet streams can be fairly sizable in their coverage, but when we look at the strongest core of winds, typically that's a lot more narrow, and that's what we see on our weather maps, this kind of strongest core of wind speed. So when we talk about jet streams, we talk about troughs and ridges, and you may have heard about us talking this before. In easy terms, a jet stream is a trough, is a dip in the jet stream. It usually implies colder air coming in, and a ridge implies warmer air or high pressure. And it's kind of this ridge. So you'll see a ridge of high pressure in the west, a trough in the east, and for you snow lovers, this is what you want to see in the wintertime, because it gives us a transport of cold air, but also moist air coming up the coast. So those are the two ingredients we look for winter storms. And as you can see on this diagram, again, there are a lot of different troughs and ridges in the jet stream. Think if you took a jump rope and had a friend holding one end, if you kind of just whipped it a little bit, you'd see these kinks kind of go from left to right. So these are troughs and ridges, and what our computer models do is they time these troughs and ridges, and if things come together just right, we'll get a winter storm. So if you're looking 7 to 10 days out and you see a big winter storm, a lot of times it's because everything comes right together. But as we get closer in time, sometimes it doesn't quite happen that way. Things are off a little bit and the storm kind of disappears. So again, it's timing of these troughs and ridges and kind of where they're located that really goes into play for our day-to-day weather. But we really can look out about a week or two and kind of get general trends as to what's happening. And in the weather briefing, I'll show a little bit about that, how we can kind of just get general weather trends, not really get too specific. So here's a nice animation. This is from NASA, just kind of showing how troughs and ridges work. You can see, trough coming off the Pacific, and it makes its way onto the west coast and eventually down into the east here, while a ridge kind of builds over the west. You can see it's almost like that jump rope I talked about. One side goes up, the other side kind of goes down. And this would be an example of our polar jet stream. But you can see kind of how it flows day to day. And you can see little, again, troughs and ridges. So on average, our polar jet in the summertime is actually a little bit north of our area. It's mostly in Canada. The strength is, it says here 60 kilometers per hour. That's roughly, I can't even think off the top of my head, but we can look it up later. On average, the polar front in the winter, the polar jet dives to the south. You can see it's a little bit stronger. But this is what brings in our cold air during the winter and causes it to retreat during the summertime. And again, in the wintertime, it's much more energetic, much more of a temperature difference between north and south. So that's why it's typically more of a player in our weather in the wintertime as far as storms is concerned. In the summertime, as it retreats north, we get a big ridge. That's when we get our hot and humid weather. So to show in the wintertime, again, we have different things called the Arctic Oscillation. This is looking at the Jetstream pattern. So you may have heard of the polar vortex. This is something that's always there. It's what's called a semi-permanent low pressure area centered somewhere near the North Pole. So when we're in a positive Arctic oscillation, things are stable. So think the polar vortex is kind of contained around the poles, the cold air is contained, and pretty strong jet stream going essentially from west to east. So in this situation, we're bringing in Pacific air, typically seasonable or mild air, really no cold outbreaks. But when we get to a negative phase, what happens is we get a little more what's called amplitude, so more troughs, more ridges, and you can see those here. The cold air is allowed to move farther south. Sometimes a piece of this polar vortex will actually dip south over us. That's what happened over Texas last winter when they had the unseasonable cold. So these are things that we look for maybe a week or two out that can kind of tell us kind of trends. You know, what's the favorable weather trend? Are we going to get cold, potentially stormy, or is it going to be kind of mild or seasonable? So this is one index out of many, many indices that we can look at to kind of predict our weather a couple of weeks out. Here's another way of looking at it. On the left is the positive Arctic oscillation. You can see the cold air is kind of bottled up near the poles. Storm tracks are kind of out over sea because we're in kind of a more west to east weather pattern. Whereas in a negative pattern, the colder air can make its way down into the continental U.S. Frequently, we'll have more stormy weather too in our part of the region. But you can notice what's interesting in a positive Arctic oscillation, we're typically, seasonable, maybe a little cold and dry. Europe tends to get more of the action, the warmer and the wet weather, and it kind of reverses itself. We both get cold in the negative phase, but they tend to be a little bit drier. The storm track displaced a little bit further south. So one thing we can look at are satellites to help detect the jet stream. And this is an example right here. This is looking at kind of an air mass, what's called detection. So in this loop, you can see we have a cold, dry air mass here indicated by the kind of the oranges and some of these even whites in here. And then you've got this other area moving up from the Pacific, which is warm and moist air in this kind of green shading with some clouds. And it's the area in between. That's where the jet stream is running. So we can see, kind of point out with my cursor here, you can see the jet stream running around down here and then also coming in off the Pacific. So it's running off the Pacific to the plains and then into kind of here in the Northeast. So you can kind of eyeball the difference between these two air masses is where the jet stream would be located. So the Winter Blitz of 2015, I think some of you remember this. The snow lovers will rejoice at hearing this. But this was caused by a kind of a persistent jet stream pattern. For those of you who may not remember, we had in the Boston area 4 major storms in less than 20 days, starting late January to about the middle of February, smashed a 30-day snowfall record for the city of Boston, 94.4 inches. Which smashed the record of about 59, which was set in 1978. And we ended up breaking the seasonal snowfall too, 108.6 inches for the season, which was an inch above 1995 and 1996. And just, pretty much historic stretch of winter storms in eastern Massachusetts. Well, why did that happen? It was a blocked jet stream pattern. We had a very persistent trough here in the eastern United States, as you can see, the air coming right out of the North Pole. And at the same time, we had this high pressure ridge, which was located off the East Coast. So the two of these features led to just tons of Arctic air coming down and also Gulf moisture working its way into the region. So you had the clash of this Arctic air, Gulf moisture. You had a constant train of these low pressure systems coming up from the southeast every, say, about 5 days, 3 to 5 days. And this led to a succession of major winter storms over this 6-week period. Pretty unusual for that to happen. Normally, our weather comes in about 4 to 6 week cycles and isn't this persistent. You'll see this maybe for about a 3 to 5 day period. We get one storm, maybe two, and then it moves on and we kind of relax a little bit. But this was just really a very, very persistent weather feature. So that's the main reason why we were so stormy and cold as well. If you remember, behind a lot of these storms, we drop below zero across much of the region. So that really kind of helps to explain the whole pattern right there. Now, one thing I've been asked a lot of times is, how about climate change? How is that going to be, is this a result of that? And honestly, the jury is kind of out on that. we have to really look, wait 20, 30 years to kind of see, are these things that are happening kind of outside of our normal signals? We have a lot of global circulations that impact our weather. El Nino, La Nina is one of them. The Arctic Oscillation is another. There are literally dozens of different things that come into play. Climate change, I think, is certainly one of them, but to separate that signal out from everything else is going to take a good 20 to 30 years of data before we can conclusively say it has an effect or not. And there's been some recent, I know the Washington Post just put out an article a few days ago saying that, maybe the melting of ice over the poles isn't totally related to climate change. The models aren't really showing that being the case. Not to say it isn't, but just to say the jury is really out on a lot of this, and we can't put blame one weather system on climate change. It really takes years and years of establishing a pattern to see if anything is there. So in a nutshell, we just don't know right yet whether or not climate change is going to play a role. So one thing that happened during that time is you can see that persistent low pressure. Look at the land and ocean temperature departures. This was February of 2015, and we were pretty much the only spot on the globe where there was significant cooling. Look at the warming in the west, and that's our ridge of high pressure right there in Alaska. Alaska had record warmth while we were shivering below zero. But look at how much more of the globe was above average. Northern parts of Asia, Europe. They were all basking in record warmth. Even parts of Africa, parts of Australia, the southern hemisphere. It was just our area of the United States and adjacent areas of Canada that were well below normal for February of 2015. So that was kind of an interesting tidbit that we discovered. Some other recent weather events here. Upper level winds. This is it's a little hard to make out that map. I apologize for that. This is an animation. So essentially, here's Alaska and the West Coast. You can see a number of strong jet streaks, as they're called, which are kind of strong winds located within the jet stream, moving across the country. So here's some impacts in Hawaii from a strong jet stream. You can see as the animation goes. This is what's called an atmospheric river off the Pacific. Look at the long train of moisture coming off the Pacific, bringing that in. And sometimes those can get into the Gulf Coast and even the eastern U.S. under the right conditions. But you can see there was rains in Hawaii, California, and also up near Seattle. They had northwest snows. So it's the jet stream that really helps provide the moisture and the heat or energy for these things. And these three, events that you might think are kind of separate, snow, Hawaiian rainfall and California rainfall, these were all linked by one strong jet stream over the Pacific. Now, a little bit closer to home, this again, as I was talking about, this was the record cold from Texas last February, and you can see an image there on the lower left. These were the temperature departures from February 15th to 22nd. The core of the cold air dove right down into Texas. And why did that happen? Well, right here at the jet stream, you can see you've got an enormous dip in the jet stream here. You've got strong winds coming out of the Pacific Northwest. This is actually supplying some Pacific moisture, believe it or not. And then with this massive dip, you're allowing all this cold air to come right out of the North Pole and Canada, bringing unseasonable cold into portions of Texas. Whereas our area, we're on the east side of this big trough, and we're getting warm and moist air out of the Gulf. So we were actually not too cold during this spell. Sometimes the trough will rotate east, and we'll get into it, but in this case, it kind of lifted out across the Great Lakes. So the core of the cold air, as you can see here, went from Texas and ended up kind of exiting North America through the Great Lakes and eventually Canada, and kind of bypassed us. We only got really clipped by some of that cold air. So another concern, if you like to fly, is turbulence. And we look at the jet stream all the time for areas to forecast areas of turbulence. This is actually from today, but let me show first, kind of where we look. Here's your jet stream core. This is the cross section, and we look for areas of rapid wind speed change with height. So areas maybe you're starting low and increasing, going to your cruising altitude as you're coming into the strong jet stream from lighter winds to very strong winds over a short distance. That's a turbulent area. Also, when you're exiting, so going from these strong winds, maybe the aircraft's getting bumped, the pilot requests a change of altitude to go higher. Well, coming out of it, going into lighter winds, you're going to get bumpy. So Going in, coming out are areas where we tend to have a lot of turbulence. And here's an example from today. Actually, a forecast of turbulence from West Virginia all the way here into New England. And you can see the jet stream. The peak was kind of at about 36,000 feet today. But you can see a pretty good dip in this jet stream here. Centered, the axis is kind of across the Great Lakes and the lower Mississippi Valley. But a pretty rapid change of wind speed with height. This was where the speeds were maximized. So coming into this layer from below or for above, any aircraft going in and out are going to have quite a bit of turbulence. And in fact, I saw several pilot reports from New York State, New England, of moderate turbulence. And that's a little more than just being bumped around. That's where you really have to be buckled in and things can get bumped about from our area. And that's a result of this strong jet stream in excess of 100 knots, 110 miles per hour. It was well forecast, but still, sometimes the aircraft will still go in and out of this area and you'll experience turbulence. So now let's turn our attention to low-level jets. We'll finish up with this, and then I'll answer some questions. A good example, I went through some of our past cases to see if we could find something. We went back, if you go back to 2015, it was actually August 4th, so the anniversary will be tomorrow. We had early morning severe thunderstorms, if some of you folks remember. This was in Rhode Island and southeast Massachusetts during the morning. Later that afternoon, we actually had large hail across most of Massachusetts, north of the Mass Pike, and into Boston itself. There was actually golf ball size hail in the city that afternoon. But for the morning, we actually had quite a bit of tree damage, wires down, and power outages south in the southern areas, Rhode Island and southeast Massachusetts. And this was a good example of a low-level jet. So first, let's take a look at what happened at upper levels. You can see we had this upper-level jet, the strongest area shaded in blue from the Great Lakes going into New England. So what this does is it provides kind of larger scale lift over much of the region. In other words, the air has to go out at the top of the jet stream. So as it goes out, air has to be drawn upward, and that's where we get our rising motion from. And you can see another classic sign is there was an upper level low here in southern Canada. This is a pretty common signal for severe weather in the Northeast during the warmer months. So in the winter, we might think, oh, it's going to be cold and maybe some snow. But summertime, this could be a good severe weather signal, including 1 or 2 tornadoes in the region. So first we have is our upper jet, providing a lot of large-scale lift across the region. But we have to look at some of the other ingredients, especially lower in the atmosphere, instability, moisture, those sort of things, to see if things will come together. So now let's go down to 2,000 feet. This is our lower level jet. And you can see I shaded here in yellow. There's actually, and I'll zoom in a minute, it's actually present off the New England coast. You can see each of these wind barbs, as we call them, are wind speeds. So we have 10 knots on the long ones, 5 knots on the short. So you've got 10 knots here. This is Albany, 5 knots, 10 knots at Gray, Maine. But if you go down a little bit off the coast, on Long Island, we've got 30 knots. Chatham at the time, 25 knots. And here in New Brunswick, it's about 25 knots. So you've got a band of stronger winds here at 2,000 feet right off the coast. And what this does is 2 things. First, it provides a little more lift, but it also provides moisture, which we need for thunderstorms. And we'll get into that a little bit next. So if I zoom in here, you can see on the left, there's our low-level jet, again, showing about 30 knots, 25 knots, kind of focused right along the coast in the yellow shading here. Now at the surface, this is our typical surface plot. You can see this is about 4 or 5 in the morning. It's a pretty warm and humid night. Temperatures are in the mid-70s. The dew points are in the low 70s, so it's pretty sticky. But the winds at the surface are light as well. A lot 5 knots here, maybe 10 knots, so very light winds. This is what we call decoupling. So there's a bit of an inversion, which is an increase of temperature with height. We're not mixing like we do during the day when we get our typically gusty winds. At night, we get this nocturnal, what's called inversion, where the strong winds kind of remained aloft and they don't mix down to the surface. And that's exactly what's happening here. So typically we think not much is going to happen, but that low-level jet can really get things firing. And if you look at this radar from about 5 a.m., you can see we've already got some thunderstorms here on the radar across eastern Connecticut, getting into Rhode Island and parts of Long Island as well. And why is that happening? Well, this low-level jet is providing some added lift on its edges. And at the same time, we've got some instability. This is the what we call the CAPE or instability. So the higher numbers mean more unstable air. And you can see the axis is offshore, but we do have a good amount of instability here working into eastern Connecticut, Rhode Island, and southeast Massachusetts. So the combination of these 2 things, instability, lift and moisture from the low-level jet help these thunderstorms to develop at a time you probably wouldn't think it's too favorable. And this is actually pretty common in the summertime. Forecasters call this our sunrise surprise a lot of times, because about an hour before, there was virtually nothing on the radar. And I remember the midnight shift telling me, yeah, we didn't think much was going to happen, but boy, we saw that instability, we saw the low-level jet, we figured stuff was going to start to form, and boy, did it ever, right at about 4:30, 5 o'clock in the morning. And as I go a little further in time, here's about 7:24, you can see the storms have made it into Rhode Island. Nothing that would say maybe they're doing a lot of wind damage, but, still pretty impressive. But look at this is the base velocity, and the Taunton radar is right up here on the top of the image. These purples are 70 to 80 knots of wind at just about not even 1,000 feet off the ground. So you're talking winds roughly, 80 to 90 miles per hour around Cranston and Warwick. So no wonder there's quite a bit of damage. Meanwhile, around Westerly, we had winds of 60 to 70 knots. This is a little bit higher up now. You're up at about 15, maybe 2,000 feet. But as these storms move through Charlestown, there was actually an 83 mile per hour gust to the weather station, and there was injuries to 10 campers in a campground early in the morning. Most campers were not expecting severe weather. It came on very quickly. So again, a good example of how we can get severe weather under the right conditions, courtesy of an upper level jet, but more importantly, our low level jet. So it's a pretty interesting case. We don't see too many of these in the summer, but occasionally they do happen. If they do happen, it's usually about this time of year, August or late July. So with that, let's take a look at our Jetstream 101. What I'm going to do now is pause here, and I'm going to answer all of the questions. So I will go through the chat and kind of answer these as we go along, and then we'll do a quick weather briefing, and we'll actually take a look at the Jetstream and see how that's going to affect our weather. So let's see, from Linda, a comment, a friend who has an oceanographer says they can already see a slowing of the Gulf Stream due to the rapid reduction of the Arctic ice. Okay, thanks, Linda. That's certainly an effect of that. So not my total area of expertise being a meteorologist, but I did take some oceanography. So there you go. And the slowing of the Gulf Stream, what is that going to do? Well, that's going to give us more energy as we get, in the winter storm season. Warmer waters slowing down, keeping it around longer. So you have, low pressure systems staying over the Gulf Stream on a longer time scale than they normally would. So great comment. Thank you. Since Linda also says, since ocean temps affect the jet stream, and indication that the jet stream is also changing. Some indications, Linda, that we're getting more blocky patterns, like I showed from February of 2015. There's definitely a correlation. We know that through El Nino and La Nina. The time scale is usually over a few weeks or even months, as opposed to direct day-to-day correlation. But yeah, there's certainly indications that the subtropical jet stream in particular is getting a bit stronger. It's got a little bit more energy to work with in the areas of the Pacific and areas of the Gulf Coast in particular. At the same time, the polar jet stream has more energy to work with too. As you mentioned about the Gulf Stream, there's more of an energy temperature difference. So, there are indications that we've seen more, of stronger jet streams on occasion. So, again, something that the climatologists are looking into, and it's going to take a number of years to really come to any significant conclusions on that. But anecdotally, yeah, I would say, to me, looking year to year here, that is certainly the case. Let's see. From Ethan, he's got some questions related to our outage. So Ethan, do me a favor, you can email me with those, and I can give you more information on that. So you've got my email, I know that you do, so we can talk about that. Or maybe at the end I can. So Ethan wants to know, do the jet streams vary significantly in height? They do. In the summertime, the core of the jet stream is higher because the atmosphere is warmer. So again, today it's about 36,000 feet. It can be up around 38, 39,000 feet. In the wintertime, it gets a little bit lower. The atmosphere is colder. It can be as low as maybe 30,000 feet or 34,000 feet. Not much of a difference, but on the order of about 5,000 feet or so, typically we'll see that variation. Katie wanted to know, was there a tropical cyclone in the NASA animation? Yeah, I believe there was. I would have to go back and look at that. But yeah, that was over a long period of time. So you probably did see one or two tropical cyclones in there. Good catch. From John, is the intensity of the wind in the jet stream consistent along its length, or does it vary as it travels around the world? It does vary. So you typically have a corridor of strong winds. And as I mentioned, you have what are called jet streaks, which are kind of pockets of higher wind along that jet stream itself. So think you may have a jet stream running maybe 80, 100 miles per hour across the country. There could be a jet streak with a smaller area of maximum winds, maybe 125 or 150 miles per hour. So those jet streaks are kind of what we look at as well for a little bit of enhancement when we look at added. I talk about lift with, say, winter storms. That's one area we look for, those jet streaks in particular. So yeah, there are normally pockets of stronger winds along that river of air itself. Good question. So let's see, from Katie, recall reading somewhere when two jet streams phase together is when we get a lot of our most severe winter storms, as that is when most energy is available and they possibly, hopefully, trek near the coast. Correct. So in the wintertime, we also look for phasing of the polar jet with the subtropical jet. And that just means when there's a trough in the polar jet, there's also a trough in the subtropical jet over the same area. So think about the East Coast, for example. We look for, you might see in our forecast discussions, we talk about phasing, and that's exactly what we're talking about. If they phase, we tend to be able to get a stronger storm because you're combining the energy between the two. You're combining the cold and the moisture at the same time. If they don't phase, and we see that happen a lot, storms get kicked out to sea or they move through quickly. They don't really develop maybe until they get to the Gulf of Maine where there is phasing. Then we get a weaker storm. So definitely. Good observation, Katie. And that's something to keep an eye on as we get into winter storm season. Do the jet streams phase? That's when we typically get our big storms. Comment from Jonathan, 2015, above average SSTs in the sea surface temperature in the Aleutian Gulf. Absolutely. That warm water in the Gulf of Alaska contributed to the anomalous block and kind of kept it going. So again, it's that we have that interface between the ocean water temperature and the atmosphere. It's an ocean atmosphere connection, in other words. So yeah, great observation. Let's see, from John, what is the life cycle of the lows that travel along the jet stream? Usually stops tracking after they move offshore. Do they make the trip around the world and come back to us? Usually not. In a lot of cases, it depends, again, on the situation, but the longest life cycles, you might see a low come in off the Pacific, travel across the country, give us a good snowstorm, move off to the Maritimes, a good snowstorm there, and go off to Europe. It's not unusual. It just depends kind of on how the steering currents are aligned. Again, how is the jet stream aligned? In some cases, we might just get a quick shot. The storm might form off the Carolina coast. We see that a lot and move up here. Really just depends on the jet stream pattern at the time. So I don't think I've seen one come completely around the world, but a lot of the jet stream energy aloft can actually do that. And we watch those over a couple of weeks at a time. That can certainly happen. From Suzanne, why does a jet stream form instead of just a blending of temperature and pressure? Again, it's obviously a complicated process, but the jet stream forms as a result of temperature differences. That's how wind forms. So you've got the heating of the air at the equator, less heating of the air at the poles. There's a temperature difference. We have the Earth's rotation that comes into play. So that's really what comes into forming the jet stream. If we didn't have any Earth's rotation, if the Earth just stopped, obviously we'd have a lot of problems too, but we also would have no jet stream and no weather. So it's all of those things combined that come into play. And yeah, the temperatures certainly come into it, but it's kind of steers what happens at the surface here at our on the ground when we're looking at highs and lows and cold fronts and all those kind of things. From Stephen, what was the effect of changes in jet streams on this summer's odd weather, unsettled and heat waves? Yeah, so I think we talked about this in one of our event reviews, but really over July, we had a very persistent trough here in the eastern United States. So the axis was kind of near the eastern Great Lakes, which is a good setup for us to get a lot of moisture and a lot of warmth in here. Not overly hot weather, but enough to keep the tropical air coming up from, say, the Bahamas or the Gulf of Mexico, and adding that moisture, adding that warmth, that kind of stalls cold fronts over us too. It doesn't give the cold front a push offshore. So if you remember around the July 17th to 18th, we had the flash floods. We even had the EF0 tornado. That was the effect of a stationary front sitting pretty much along the Mass Pike and, wavering a little bit south and north, but that was our focus for thunderstorms. And as long as that trough sat there, we were going to keep continuing in that weather pattern. So we had showers and thunderstorms, just about every day through early and mid-July. And finally, the pattern changed itself where that trough kicked off to the east and things moved along again. But that happens, on occasion. So that really was the main effect, Stephen, for last month. From John, is lift generated from the jet stream part of the equation for calculating CAPE? Not really. CAPE is more just the instability or the energy that's available. It's essentially from heating. So the lift, we look at the jet stream more for looking at the wind shear or the change of direction with height or change of speed with height. So it does come into the formula for severe weather, but not so much for calculating CAPE. It's more about the wind shear. From Catherine, let's see, are the quadrants found in the jet streak instead of the jet stream itself? Yes, kind of both, Catherine. So if we're looking at what we call the entrance region, the southern end of the jet, or the exit region, the northern end, there are areas that are favored for lift. So we're looking in jet streaks, which are those local maximums within the jet stream itself, but also on a broader scale in the jet stream. So I showed a lot of examples of kind of the broader jet stream. Sometime more in the wintertime, you see these jet streaks form. So kind of look at both, but more so if you see jet streaks, because there's stronger winds, they can induce more lift in the atmosphere, if that kind of makes sense. From Ethan, where can we find those maps with the observations at different pressure levels? Those are from the Storm Prediction Center. So if you go there, Ethan, go to the archive page. You can find all of those there. It's a nice plot of kind of the wind speed at different levels, low and high. So you can check Storm Prediction Center. From Katie, with the stronger winds aloft and different wind speeds at different altitudes, would that be classified as a type of wind shear on the 2015 severe event? Yes. And actually, I didn't show the sounding, Katie, but yeah, that's correct. So we had kind of a northwest flow, remember, aloft, maybe at 35,000 feet, and a kind of a southwest flow or even southerly flow at the low levels. So yeah, you have what's called directional shear, change of wind direction with height, and also a change of speed with height, going from that 20 to 30 knots in the low levels up a lot higher. I think it was 40 to 50 knots. At the higher levels. So yeah, that is considered a type of wind shear. We look at both direction and speed changing with height. And there you go, Katie, vertical wind shear. I see that. So let's see, from Ethan, is it possible in our area to get very high shear with a very powerful upper jet stream with very high CAPE? Yeah, and an example, Ethan, go back to June 1st, 2011. That was a day where we had tremendous amounts of what's called CAPE, or again, it's just think of instability. We were on the order of about 4,000, which is pretty tremendous. That's more like the plains. And we also had a very strong jet stream aloft, which led to very high directional and speed shear. So that's an environment very rare here. Maybe, in my opinion, a once in 50 to 60 year event. It's more typical of the plains where, Oklahoma, Kansas, think of those areas where they get a lot more severe weather and high-end severe weather with tornado outbreaks. So yeah, it does happen, Ethan, just very, very rare in our area. Let's see. Katie's just got a question. Oh, for Skywarn. Okay. You know what you can do, Katie? You can just, we don't really need, necessarily the Skywarn report. So you can just go get us on social media, Twitter, Facebook, or also by using the submit my report on the webpage. But social media is probably the quickest way, Katie, and for anybody else. If you're a Skywarn spotter, you lost your card, no need to retake the exam. Just catch us on Twitter or Facebook. That's perfectly acceptable. So from Brian, what is the best website to view Jetstream maps? I kind of like the Aviation Weather Center. If you go to aviationweather.gov, you can view it there. And that's where I took a lot of the maps. The Jetstream map for today, for example, was taken from there. So aviationweather.gov. That's the Aviation Weather Center, and they have some nice maps. You can click on the forecast for wind speed, and you can go up and down through the atmosphere using up and down arrows. Pretty cool interface that they have there. So I would recommend that. So let's see. Jonathan's giving me an equation here. Polar amplification equals more exposed ocean. Warm feedbacks equals decreased meridional potential energy, weaker, higher amplitude, mid-latitude flow. So let's see. When you have amplified flow, you get a lot more the ridge over the Pacific. That's your warm feedback. If it decreases, you have less of a feedback mechanism. So more zonal, what we call east to west flow, which is weaker and doesn't give us as much energy. I think that's what you mean, Jonathan. If not, just throw me a note in the chat. Let's see, from Sebastian, climate change is such a complicated issue. Yes, it is. There's a lot, and there are so many variables that influence our weather. You can't just point to one or the other. Even in forecasting, we do these seasonal outlooks where we look at maybe a handful of indices, and it's not enough. So it is very difficult to kind of take that out from the normal climate signal, Sebastian, but that's where our computer models come in. That's where our climatologists come in. So again, a little bit out of my normal, lane of expertise, but certainly something that's being studied by our climatologists. So question from Greg, briefly touched upon using Arctic oscillation predictions. We did. What is the main mechanism for North America dynamics, and what is the limitation for the forecaster for the longer term predictability? The Arctic oscillation will give us general trends. It doesn't mean you're going to have a storm either. It just kind of trends us cold and usually more stormy, but doesn't always happen. I can point you back to a lot of the case studies we've done that those were in place and kind of nothing happened. So we're limited by just, we're not going to use just one index either. It's again, as I mentioned, a bunch of different things come into play. So there's really, when we talk about the main mechanism for dynamics in a storm, it's looking at the jet stream, it's looking at jet stream patterns, which the models do pretty well, but typically the predictability for that is only about 3 days. We talk about that a lot in our forecast discussions. Energy coming down from the Arctic, energy coming onto the Pacific coast doesn't get well sampled until it reaches the West Coast or gets to the United States. So that's usually about 3 days. Sometimes 4 or 5 when we can really start to see trends on that. I hope that answers your question, Greg. If not, you can throw me another chat there. So John wanted to know the weather pattern for July 2021. Was that similar to January, February 2015? Yeah, but on a kind of a lesser scale. It wasn't quite as deep. As I showed in the images, the western region in the January, February was just tremendous, and that really dug a strong trough here in the east all the way down to the Gulf Coast. In this case, the trough was over the Great Lakes down to maybe the Ohio Valley. Was a bit weaker, and that's typical in the summertime. We're not going to see these giant ridges and troughs, so much in the summer because the temperature contrast is just lower than it is. From Brian, why does clear air turbulence tend to be on the northern side of the jet stream? Again, it has to do with coming in and out of where the strongest air is, and kind of things to do with directional shear too, or speed shear. It is on both sides of the jet and over the jet itself. So you got to kind of think in 3 dimensions, not just on the north or south, but in the vertical too. So it's kind of all around. But the favorite area tends to be on that northern side where the air is kind of exiting, if that kind of makes sense. Let's see, a few more. Let's see. Greg, do you have any desire to do a webinar on the recent tornado outbreak in New Jersey? Yeah, we actually had a briefing on that the night before, if you guys remember. We actually did Rodney and I did a live briefing. I'll see if anyone's going to do anything on that. I know at Mount Holly they're working on that, and we can kind of see what they're up to. We can certainly present what they have, but yeah, that was a tremendous case. Just a high number of, I think they had 9 tornadoes in that area. I'm not sure. I got to check with our team and see if usually someone from our team will do one as well. So I'll check around, Greg. We can certainly do that. I can certainly schedule something later in August. And if the Mount Holly office doesn't have anything thrown together, we can certainly do that. No problem at all. I will make a note of that. Good suggestion, Greg. Thank you. So from Wayne, does the NAO influence the AO, and what is the correlation? They're 2 different things. So the Arctic oscillation is kind of the bigger player. It's more of a global circulation. The NAO is the North Atlantic oscillation. So it's a more transient thing. Think in terms of a couple of weeks as opposed to maybe 3 or 4 weeks at a time. It's more about 1 to 2 weeks. And it's just looking at essentially the North Atlantic, Greenland over to the Azores. So it's kind of, think of it as a subset of the AO. It's looking at the same kind of, it's looking at pressure differences between Greenland and the Azores, whereas the Arctic oscillation is looking at more of a larger area. So it's kind of a subset. if that kind of makes sense to you. But we use the NAO as more to kind of tell, it's more transient, as I mentioned. So you're looking at maybe a week, 2 weeks tops, as opposed to the AO, which can go several weeks. And from Landon, what is phasing? Is it just when jet streams merge? Yes. So phasing means you have the polar jet and the subtropical jet kind of in the same shape. They're both in a trough in the same area. And that's when we get our bigger storms. So let's see. From Sebastian, a lot of great questions. Thank you, by the way. The 3D diagram you show the jet stream looked very similar to Hadley cells. Yes, that's exactly what I was showing, Sebastian. That is known as the Hadley cell. I was trying not to get too technical, just keeping it simple. But those are results of the jet streams. So those are the circulations that we see across the globe. Let's see. Jonathan's got a suggestion for Rodney. I'll have to pass this on. Got to check out Snow by Charles Wood, the new Snow Bible. All right. I have heard of that, John. We'll do. Maybe I'll have to get an office copy. From Katie, having that kind of setup where the jet stream is set up like that, bringing tropical air up, like it has been for so long till recently, can bring up any tropical systems like Hurricane Bob. Yes, that is another concern. That's why we also had Elsa in there, Katie, if you remember, in July. So something we're going to be watching. The tropics have kind of settled down a little bit for the time being, but it's going to pick up. September's the peak. So as we go through August, we'll have to watch, and we'll have to kind of look at the jet stream pattern. Is it more up the East Coast, which favors us getting a strike or at least a pass nearby, or is it more east to west, which is going to push everything out to sea? So keep an eye on the jet stream too. For those of you keeping an eye on the tropics, you can usually tell within about a week what the pattern's going to do. So that will kind of, tell us as far as our landfall potential. Let's see, from Landon, relating to the previous question, since lift is not included in CAPE, is there an index we use to assess lift from the jet stream, frontal forces and other sources? Yeah, the models actually show that, Landon. If you look at the model output, it's something called omega, and that is just a term we use for lift. So take a look at that. That is related. That kind of takes into account all the different processes going on, whether it's heating of the ground, whether it's from the jet stream, whether it's from a trough approaching. We get lift ahead of a big trough. That's what the models will calculate. It's the omega term, as it's known. So that's usually available. If you look at most of the model sites, you'll find that on there. Usually, if we're looking at the millibar level, 850 to about 500 millibars is where you look for that. So good question. Let's see. Max wants to know what Skywarn is. Skywarn is our volunteer network of severe weather observers. So if you go to our website, weather.gov/Boston, and look under Skywarn, you'll find out information on becoming a trained weather spotter. So we've been doing virtual because of COVID, but we do virtual training where you can learn how to recognize different severe weather features that are common here and report them to us. Also a little bit of weather safety. So we typically do those in the spring, Max. So check the website. Sometimes we do them in the fall or winter as well for winter weather spotting. But Skywarn is just a volunteer of weather observers, so you're welcome to join that. All right. That is all the questions for now.